Good morning, everyone. This is Randy from Central Region Headquarters. We're going to go ahead and get started this week's Wednesday guest speaker series session. Today, we're fortunate to be joined by Dr. Patrick Market from the University of Missouri, Columbia. And Dr. Market has done a great deal of operationally oriented research, including jet streak frontal interactions and heavy rainfall and snowfall forecasting. I first got to know Dr. Market through our interactions at the NWA, actually. And one thing that I really love about Dr. Market is he's really one of the operationally focused folks in academia. He does tons of academic or operationally oriented research, so we're really fortunate to have him today. And today he's going to be talking about DCIN and DCAPE to anticipate severe surface winds with elevated convection. Dr. Market, thank you so much for joining us today, and the floor is yours, sir.
Well, thanks, Randy. I appreciate it, and I appreciate everybody for being on today. Thanks to Randy for having me, and I don't know if Ray Wolf is out there or if he's catching some Z's, but it was Ray's idea, suggested me to Randy for this opportunity. So I'm glad to be able to have an audience for this for just a short while. I'll say also, as a means of introduction, I am a professor of atmospheric science, but the last few years I've been doing more administrative duties. It's something more than a department chair and not quite a dean, so it's a nice opportunity to actually talk about science for a little bit. With that, though, I've also learned from some of my colleagues that less is more, and I'm not one to make a 15-minute conversation out of a 5-minute conversation. So I plan to take just enough time to present this DCIN idea, and we'll move on. To start with, I have to thank a couple of students, alumni now, Paula Summerall, who's taken a job in private industry, and also Kevin Grempler, who's at OU and Sims and working in a research capacity there. And also a couple of weather service supporters for a very long time, Jason Chauman at Springfield office, and also Dr. Greg Mann. Each of them brought a case to our attention. We've been doing some work on this DCIN idea for a while, and so what I really want to do today is just kind of touch on what it is, and then a couple of really quick cases that we've done. There's a lot more out there, but I'm trying to keep this again short, and then just some idea of where to find this product, and then a little bit on what we hope to do with this in the future. So again, a quick outline here, 2 cases, one from the Springfield area, and then another one on the Michigan meteor tsunami, which was a phrase I hadn't heard until Greg brought that to my attention. So those have been very interesting to me as well. And then again, finding the data in real time, and then hopefully plenty of time for questions, and maybe even, we can build in a coffee break for you as we get close to the end. So a really quick foray into what are DCAPE and DCIN. Everybody knows DCAPE. It's been around for a long time. And frankly, so has DCIN. It's just really nobody paid attention to it. The first time that we started working on this and getting it to the point where we could visualize it, and had one of our undergraduate students refer to this as a discovery, and I'm like, nah, I appreciate your enthusiasm, but I think it's been around for a long time. Really, just nobody's paid much attention to it until now. So this is all done in the context of, either prefrontal convection, elevated convection in the last decade or so has taken on a much broader context. But in either case, what we're talking about here is the creation of a near surface stable layer, whether that's, the decoupling of the boundary layer from the free atmosphere, or something happening north of a frontal zone. Most of the work that we've done has been in that latter area, and really kind of looking at what happens north, especially of warm fronts. But at any rate, so our approach, and I'll talk a little bit about this later on, is to use the parcel that initiates in the lowest 6 kilometers where the coldest wet bulb temperature happens to reside. So in this case, that's what we're calling Z sub n. So that's the origin level, and I'm assuming my mouse is showing up here. But we're looking at the SKU-T now. So that upper layer, that level, I should say, that's marked Z sub n. And then, of course, we have this dark purple area here. Now, I'll say, too, I'm indebted to John Shuchuk at RAOB. I contacted him. I toyed with the idea of working through this in the older version of N#. Had a grad student who got close to having this render in SharpEye, but I don't know that we ever got that done. But John was able to turn this around on the dime. And there are some other nice features that he put into RAOB. So if you have access to RAOB, a more recent version, then you can do this. And of course, you can even put, in the upper right-hand corner, there's all the metrics that he typically puts in there, but the DCIN and DCAPE in this case show up here. So the dark purple layer is the DCAPE, and that's the layer of negative buoyancy. And then in the case of having a stable layer, Z sub NB is going to be the level of neutral buoyancy, and then beneath that level, then that's actually positive buoyancy, because at that point the parcel is warmer than its environment, and so of course it should be slowing down. It's really I like to describe it as sort of looking at an overshooting top, but then just inverting the entire sounding, right? The parcels eventually stop rising in a thunderstorm because they're colder than the environment. In this case, the parcels eventually stop descending because they're warmer than the ambient environment. So with that, that's pretty much the idea behind DCIN. And if you look at the expression, really the only thing that changes are the levels or the limits of integration, however you want to refer to that. So that's the sounding view. And of course, then in addition to that, what we also were exploring, and we'll look at this in sort of a plan view area here in just a moment, is the ratio of the two. So, if you're just using pure parcel theory, and I'll back up here for a moment, if these two areas are of equal size, right, then ideally, just as your parcel is arriving at the ground, it should have a velocity of 0. And so that would be a DCIN and a DCAPE having, the same value. And so that gives you a ratio of 1. So the working hypothesis that I've had students, take to task in the last few years has been this idea that as that ratio decreases and approaches 0, then the likelihood of there being strong winds occurring at the surface is going to increase pretty dramatically. And there's some other things to be explored there, but we're also not, well, I'll come back to this later, but we're also not including things like, precipitation loading and, the actual evaporation of droplets as you get, if you get beneath cloud base. So those things really haven't been included at all. There's also the issue of wave motion, but we'll see that in these two cases that we're going to look at. So yeah, you have to have a sounding profile, right? If you're going to do DCAPE or DCIN, sounding profile is going to be necessary really to create that. So there are really two different ways that you can visualize this, sort of on a point basis or a plane basis. So point, of course, being locally through something like a sounding or a SKU-T, whether that's observed data or from model output. And then, of course, regionally, anything, you can look at CAPE in a sounding or you can plot it. So, this is really no different. And we have some examples of that here. I have some examples that I'll show you here in just a little bit from each of these cases. So the first one is the one that was suggested to us by Jason at Springfield. And this would have been just a few years ago. It was February 7th of 2019. There were some severe reports. I mean, it was a pretty significant case, but I don't know that it's one that would be terribly memorable outside of that local area. There was a slow-moving frontal boundary just to the south of where the bow echo occurred, and there actually were gusts measured that were in excess of the severe criteria, so 60 knots, and there were warnings associated with this. And if I remember correctly, Jason did share that they actually did look at these parameters on that evening, and I don't think they played a significant role, but they did play a role ultimately in warning decisions. So again, just a quick look at the reports, specifically on the left-hand side, wind and hail mostly. There was one tornado report further south, but that would have been in the warm air south of the location of the frontal zone. And so this is the WPC analysis for 6E. So this is right around the time that things were occurring, and you can see from the the mosaic of the radar image. And of course, that's the spot that we're looking at. So it is very close, less than 50 kilometers from the location of the surface frontal boundary. There's also an outflow boundary that's diagnosed further to the south. So, you can make arguments about where was the actual boundary defining warm from cold air. So experiencing network connection difficulties. Brandy, can you still hear me okay?
Yeah, we can still hear you.
Okay, all right. I got a little message that popped up there. So anyway, moving on. So this is a plot for DCAPE and DCIN. This is one that we make internally here, and we do make this available on the website here. I can show that here in a bit. And so what we have is 5Z and 6Z for that evening. We don't always get all of the RAP data that we need in time, so we just grabbed everything that we could. But at any rate, what we're looking at here is that the dashed red contours represent the DCAPE. The solid black contours represent the DCIN. We learned early on not to plot 0 for DCIN because it gets really squirrely, but -5 turned out to be a pretty good value to get something that you could really kind of sink your teeth into. And it turns out that that's very often not a bad approximation for the location of the actual surface frontal zone, which makes some sense, right? That DCIN really should be going to 0. You should lose a lot of that surface-based inversion once you get south of a well-defined frontal boundary. So what I've shaded here now is that area between where the ratio, which is that thick purple line, right? That's sort of the northern boundary that you're looking at here, sort of across central Missouri and into southeastern Kansas, and then almost to the panhandle of Oklahoma. So that's where the ratio is 1. And you can see here, here's your DCIN line. So there's an intersection of DCAPE and DCIN of 400 joules per kilogram there in southeastern Kansas. And so there you go, there's that ratio of 1. Okay, so north of that line, this one seems to be pretty reliable. Once you get north of that line, the likelihood of significant convective wind reaching the surface is pretty much nil. So between the purple line, that ratio of 1, and where the DCIN becomes -5, that tends to be the area where the greatest threat for convective wind reaching the surface is best or worst, depending upon your perspective. And of course, the red star in this case defines again Springfield and the location of the measured severe criteria wind. So just look briefly at some soundings, and I would draw your attention here in the upper right-hand corner, so that the DCIN and the DCAPE are in that red box. And of course, at this particular time, the DCIN is much greater than the DCAPE. This is 18Z, so this is afternoon, and they were flying additional soundings, so we're going to see, I believe it's 18-0 and 6. So this would have been an off-time sounding. This would have been a regular synoptic sounding. And notice now that the DCAPE has become larger than the DCIN. And you can visualize that here. I'll back up. And of course, it's one of the reasons we like to have the numbers to numerify it, because, why eyeball it if you can actually integrate it within the program. So at this point, midday, the DCIN is larger. By the time sunset arrives, we actually have a DCAPE that has become larger. And as we approach the actual time of the event, now we have a DCAPE that is 487 joules per kilogram and a DCIN which is only 6. Again, the frontal boundary is fairly close by. And again, this is also observed data, but the classic warm front should have a southeasterly wind ahead of it, right? And switching to southwesterly once you get on the warm side of the boundary. And we do have a suggestion of that very lowest level wind was southeasterly at about 5 knots. So frontal boundary probably was pretty shallow, but this is still more evidence that Springfield at that time was just north of that boundary. And then of course, the following morning at 12Z, winds at the surface, of course, are northwesterly, and clearly, that front has moved away, and the DCIN is much larger than it had been previously. So, just a couple of quick thoughts here. There was a steady decrease in the DCIN leading up to the time of the event, And I think that was significant in allowing severe winds to penetrate to the surface. There were some other elements to this particular case, though, that I think are important, and we're going to look at that here shortly. In fact, we'll look at it right now. So I'll draw your attention. So, the Springfield radar is, I think everybody's used to looking at GR analyst. And of course, the reflectivity is always the thing that draws your eye, but you guys are professionals. I draw your attention to what's happening on the right-hand side and the rendering of the velocity. And just notice here, the significant winds were measured at the airport. So this was an ASOS report. And you'll see as time goes on here, and this is just every few minutes, clearly there's wave motion that's present, and it's close to the surface, right? So one of the things that we explored with observational data, I toyed with including here, but I think it's enough to say this did have an influence, and we'll see this again once we look at the Michigan case here in a moment. I think there's clearly an influence of wave motion and helping to transport momentum to the surface that might not otherwise have been tapped. So, this I mentioned earlier, there's precipitation loading, there's evaporation. I think there's also wave motion to consider. We didn't quite model either one of these. What we're looking at here is the outgrowth of a master's project, and that was not an avenue that we decided to go down for these particular cases, and we should have. That's still fertile ground for someone else to explore. So a few more radar frames here. And yeah, so just a quick radar analysis. I think I kind of have already touched on this, but I do think the presence and prevalence of those wave motions, we use the phrase assist parcels to the surface, but this is something that I'd really like to tear into. And I think an ensuing graduate student, I'm down to just one or two at a time, but I'd really like to bring something like Cloud Model 1 into the fray and see if we can't model something like this and try and assess whether or not these waves actually are having an impact at the surface. Summary of case one. I won't really belabor this. I did want to point out, though, that this wasn't just a spotter reported wind, and that should be 60 knots, not 60 miles per hour. But this was a severe criterion wind, so this was a warning that actually did verify. I'll take a quick look here at case number 2. This is April 13 of 2018. In this instance, there's no doubt that what was happening in terms of the synoptic setup, this event happened well north of the surface warm front. And of particular interest in this case was an observed pressure spike, I believe from a buoy near Ludington, Michigan, on the order of about 10 millibars. Now, the actual wind, I believe, never really exceeded 35 or 36 knots. But one of the things that Greg Mann did point out was that prior to that event, it had been a sustained easterly 20-knot wind. And then with the advent of the convection arriving on site, it was a westerly wind at about 35 knots. So that's a 55-knot vector change in the wind. Still doesn't meet the severe criterion, but I think it is compelling in that, imagine a case that perhaps had been closer to the location of the surface warm front, and perhaps it had been a 4 or 5 knot easterly wind, then becoming 45 knots. I mean, we're dancing with the possibility of something actually severe occurring. And I have to apologize. I did have an image here of damage from the marina in Ludington, and that was something I wasn't able to locate. But suffice to say that it was a meteor tsunami, and there was damage to boats and a marina. I don't recall a dollar figure, but it was something of substance, and certainly enough to get the attention of the larger community. This has been an event that has been studied in several other ways, and not just through this DCIN, DCAPE, and elevated convection approach. I've included less radar data here, but we will see in a little bit. There is some evidence also of gravity wave motion that is present. In that particular case, the velocity signature is quite a bit further away from the radar, and so quite a bit further above the ground, but I still think that it's compelling enough. And I'll say this too, one of the reasons that I hesitate and ultimately didn't include some of the things that was done in Paula Summerall's thesis, which is what this is based on, is that there were much more data, observed data present for the Springfield case, and so made that a lot more compelling in ways that we just didn't really have for this particular case that we're looking at here. So again, quickly, the synoptic setup. In this case, and in fact, that arrowhead probably should be just a little bit further north for the location of Ludington. But the point here is that it is well north of the surface-based frontal boundary as opposed to what we had seen in the previous case. And here we go. So this is also the DCAPE and DCIN plot. Similar to what we'd seen earlier. Again, the red star defines the location of the event. The DCAPE is still dashed red. The DCIN actually are white lines here. I had it inversed previously, and we're looking at about 2 to 3 hours prior to the event. And I think that this next frame will show pretty clearly, although this is a bit lost in terms of resolution, but this is 12Z right here, sort of right around the middle, and so that 16Z time period that we're most interested in would be 1618 UTC, winds gusting to 36 knots, and there's pardon me, there's your pressure spike of about 10 millibars in less than 20 minutes. So quick look at some of the soundings. Now again, not having access to observed soundings like we'd had with the Springfield case, we went with RAP model initializations. And so what we're seeing here, again, running these through RAOB, we have a DCIN on the order of about 250, a DCAPE of 272. This was first thing in the morning. This corresponds to the time that we looked at in plan view just a little bit ago. And I do apologize also because for whatever reason, this one did not come with the shading on it, but this area from about, where it says LFC for the equilibrium level, of course, that's for the rising parcel, but it's right around that area where we find the coldest wet bulb temperature. So this is going to be the DCAPE area down to about 725 millibars. And then from there on down, this would be the DCIN area. So here we have roughly a ratio of 1, but the DCAPE is actually larger. Now, we look at 14Z, and now that ratio changes. Now the DCIN is larger, and unfortunately for this case, that pattern is going to persist and makes this one a bit less compelling. This is the most important time here because this is the time, within minutes of the event happening, and the DCAPE is about half of what the DCIN value would be. So still significant winds arriving at the surface, and again, we have to go looking for something that makes that happen. So pure parcel theory in this case is not going to get you there. That's one of the reasons I think we need to, again, go back and look at this through the lens more carefully of all the things that I've mentioned, but wave motion in particular. And so results from the sounding analysis, in this case, it doesn't really support the hypothesis. Pure parcel theory, like I said a moment ago, is not going to carry you over the finish line. So it actually became less likely, if you're just going to use those two values, less likely for strong winds to penetrate to the surface. And, to be fair, we're hitching our wagon to that vector change of 55 knots. The actual observed surface wind from the west was only 35. Just one image here, and I believe this would have been the Grand Rapids radar. So we're looking, the radar being situated well to the south and to the west of Ludington, where the event actually occurred. But we are seeing some in and out, toward and away from the radar. So it's not really compelling. And really, there really wasn't anything in any of the radars that we looked at, be it Green Bay for sure, Grand Rapids, and I forget the third one, but none of them really. This was about the most compelling evidence that there was wave motion there. So really not a lot to hang your hat on, but still it's enough to, gives you pause, right? As a scientist, you're looking at this and you're like, well, okay, your ratio is not getting us there, market, and yet this happened at the surface. So there have to be other things that depart from pure parcel theory that, caused this event to occur. So let's see here. So results for case two, pardon me. The ratio was close to 1, at least early on, but within the span of about 3 hours, it rose to a value of 2, which is, doesn't really support what we're trying to drive home. But again, the radar data makes us really question a second time, is there a gravity wave influence present in these cases? And, especially when you're north of a frontal boundary, I don't think that's something that you can ever discount. So those are the canned cases. The question often comes up though, it's like, okay, so I like your idea, where do I find it? Well, as I mentioned earlier, in a sounding sense, I don't know, I'll be honest, I don't know if it has been adopted more broadly. In SharpEye, it may have been. The student that I had several years ago, who's since graduated, she was working on getting it functioning, and I know that she'd had conversations with people in the SharpEye community. So I don't know if it caught on. I know that we do not have it functioning here in our version of SharpEye, and I don't think we've downloaded a build in a year. So to my knowledge, it's not functioning. If it is, I'd love to hear from somebody. That would be awesome. I do know that you can get access to these, again, through RAOB. So if you have a license for that in your office, it's a simple matter of running it through. And I'm happy to, I know John his customer service has been great, but I'm also happy to talk anybody through the process of getting this turned on. It's pretty simple. If you fool around with the CAPE at all and go from a surface base to a mean surface layer to most unstable, if you're well versed in dealing with those things in that software, then just you need to look down a little bit further, and there's information down there about DCAPE and about DCIN. So it's easy to turn on to get the shading, and it's relatively easy to get the values to come up in the tabular list on the right-hand side. So that's sort of the point evaluation. And, again, if you're familiar with RAOB, I think they've probably invested more time in the last few years in just pulling in all of the various types of sounding formats. That's probably where the bulk of his work has been, that'd be my guess, and less about, crazy things like, hey, John, can you calculate DCIN and include it? Which again, he was very good about doing, and no financial interest either. So that's point, and then we come to plan view. We do a couple of sort of regional areas. Again, having worked with Jason at Springfield and Greg at Detroit, we have 2 smaller mesoscale windows that are centered on those areas, and then we do a national version. So the link for that is at the bottom. And there's an even easier way to get it. I'll get to that in just a moment. Our version employs the coldest wet bulb temperature in the lowest 6 kilometers. That was an idea that we had originally pulled from RAOB, pardon me. And after some discussion with John and the reference materials that he was using, that seemed fine. Now, I have to stress, it's the coldest wet bulb temperature in the lowest 6 kilometers. That doesn't always mean 6 km, right? It could be 3 kilometers, it could be 4 kilometers. So that's, and the script that goes into this, and yeah, sorry, it's still Genpack, but so I'm the market thesaurus, but it works. Having said that though, one could argue that the layer that we pick is too high. One thing that I can tell you is that we do get fairly consistent and coherent maps. So for whatever that's worth to you. Now, there's another way to get it, and arguably even easier. And that is by using the SPC mesoscale analysis. If you click, I've put the orange circle up here. If you click on thermodynamics and that pull down and go for the downdraft CAPE, I think is what it's called in real time, then both of these will plot for you. And so, and I have to, I'm grateful to the SPC staff for putting this in. I'm even more grateful to Jason at Springfield for advocating for this. And making the case that this is something that he would like to see. Now, my understanding on how they make this calculation is different from our own. They use the coldest theta E in the lowest 6 kilometers as the origin level for the downdraft. And I believe actually they're actually calculating the ratio here too. This is not in their documentation, so I can't say that for sure. If somebody's here and can fill us in, that'd be awesome. I think what we get here though in the way of DCIN is probably an underrepresentation. I'll back up here for a second. You could argue that ours is an overrepresentation. This is another thing that I'd like to have a student dig into at some point to find out if there is an ideal level. But at any rate, so there are a couple of different ways to get at it, different methods, but I think the same basic idea is present there. And so I think with that, we'll just go ahead and move on. I did want to pull this up. This isn't really another case, but this is 12Z yesterday. So just a day ago, and I'm hoping that this is coming through well enough. So these were the WPC fronts, and you can see a fair amount of convection still existing to the west, and then the cold air poleward of that frontal zone. Really nothing severe happening at that time, but I'm going to go to one of our plots showing the frontal zone. So again, this is, poor man's frontal zone, but I've transposed that at that same time. And this is our DCIN plot. Again, our white contours, our solid contours are the DCIN, the dashed red contours continue, pardon me, be DCAPE. And the purple, again, is the ratio. So again, that area effectively north of the frontal zone, and until you get to that purple area is, an area potentially where downdrafts could be penetrating to the surface. But again, have to be fair, nothing severe happening at that time. And then of course, this is the same HPC or SPC representation. And these are the maps that you would have just seen. This is the SPC map from just a moment ago, but with the front drawn onto it. So, I mean, it's clearly doing its job, and it's putting the DCIN and the ratio, I think, in more or less the right spot. And so with that, just a quick summary. DCAPE's been around for a while. I think DCIN has been around forever as well. Just nobody really started paying attention to it until about 4 or 5 years ago. So what we've tried to do is to help operationalize that, and not only through the appearance of the DCIN in either a sounding or on a plan view map, but also the ratio. And then some future work for us here. Just yesterday, an NSF proposal went in to study a number of elements of a thunderstorm and thunderstorm downdraft. So this further exploration, I should say, of DCIN and DCAPE is just one component of that. A bit of observational type stuff as we've done in the past, but I think the real secrets, if you will, or at least further guidance for observational study is going to come more from modeling at this point. Very, very similar to the recent story out of Stanford, and looking at, supposedly these 200 plus knot jets at the top of thunderstorms. It's modeling, I think, is going to guide us back to an observational kind of study there as a community. I have nothing to do with that one. But what I'm saying here is that I think modeling is really going to lead us, it's going to give us direction in what we should be doing next in terms of observations, and what to bring to bear, whether it's, going with some kind of hardened drone or something like that. But to really get at the nature and the influence of evaporative cooling, precipitation loading, and then these wave influences that they're clearly there. They clearly play a role. And so far, I think we've not done adequate service to what those might be contributing to getting these elevated convective downdrafts down to the surface. And with that, I think that's it. So I'll take questions or criticism. Thank you, John Gagan. I appreciate the imagery. Figured I'd include that for you. And the link is there at the bottom to have a look at those in real time. So